welcome to our lecture on learning paradigms. Towards the end of last lecture, we had already started looking at how, let's say, we have a model trained in supervised manner on some particular data set, some particular task, or some particular domain, and we want to use it now for some other task or domain. And we said that, let's say, we have at least three choices. We can use it as a feature extractor. We can fine-tune on this target data or domain. We can also, let's say, do unsupervised domain adaptation. Now let us look a bit into these particular choices. The first choice, that is just use as a feature extractor. There we are posed with different questions. One of the very important question is, let's say we have this network here. We are seeing like this is a simplified diagram, and we are seeing is like we have, let's say, some 6 layers, right? The question arises, should we extract the features here after 4 layers, or let's say we would extract feature here, let's say after 2 layers. Of course, in practice, the networks that we work with, they have much more number of layers. The question that we are trying to ask is, does it make sense to extract features from one of the last layers, or to extract features from one of the starting layers? And the answer to this question, especially when we are talking in terms of path observation, the answer is not always that simple. What happens? Let's say we have a model trained on ImageNet, okay, and we are trying to transfer it to an earth observation data set, which is very high resolution, let's say 5 centimeter per pixel or 10 centimeter per pixel, or even 50 centimeter per pixel RGB images. There probably it makes sense that we extract feature from one of the final layers. Whereas let's say we are trying to apply on a coarse resolution image, or even let's say on synthetic aperture radar image. So we have to understand what I'm talking about, transferring a model trained on ImageNet and using this, transferring here in the sense like using this just as a feature extractor, and on the top of those features maybe we'll do some clustering or something like that. And we are using it on synthetic aperture radar images, where the basic features like edges maybe is quite useful. In that case, it would make sense to extract the features from one of the initial layers, that is maybe only after just layer 3, instead of going to like one of the final layers. Yeah, so this is one of the challenge that we are already discussing. And here in this slide, look at this carefully. The question that I have asked is not just which layer. In the last couple of minutes, the discussion that we were having, I was talking a bit more in the sense like specific layer. However, the way that this question has been asked here, this is clear that the answer doesn't need to be just a particular layer, right? It could be a number of layers. And there also one of the aspect that's important to understand is this feature extraction. We are doing this for an image wise task, that is for each image we want one feature vector, or we are doing this for some dense task where maybe we want a feature vector for each pixel. Depending on this, we might extract feature from fully connected layer, because from the fully connected layer we already get a feature vector image wise, right? Whereas if we want this feature vector, this feature representation for some dense task, that is maybe we want to later, like given the image 224 cross 224, we want to extract a feature vector for each pixel, and then maybe we would like to cluster those feature vectors and to get some understanding of this 224 cross 224 scene itself. In that case, we would need to actually extract feature from one of the convolution layers, because the fully connected layer, this has already lost the spatial dimension, right? Even let's say if we extract the feature from one of the convolution layers, it's not that we'll get same spatial dimension, like depending on the layer. Like let's say our input was 224 cross 224 cross 3, so the spatial dimension was 224 cross 224, right? Depending on the layer, it could be the case that the feature that we are getting is 56 cross 56 cross, let's say, some 112. So 56 cross 56 here is a spatial dimension, right? However, what we could do always is that we could do some upsampling, some interpolation, and we can get 224 cross 224 cross 112. Or we could simply, like repeat those feature vector for one pixel, we could repeat for a few pixels to get that dimension of the input, spatial dimension of the input image itself. And then we could proceed with whatever we want to do, clustering or some other task that we want to use this feature vector for. There also a related question is, do we have a validation data set? Maybe we have some sort of validation data set where we could do some experiments, some control experiments to decide which layer to extract the feature from. One of the natural choices in this context is formation of hypercolumn of feature. That is, instead of extracting feature from one particular layer, why not take all the layers, or even if not all the layers, let's say a large number of layers. Okay, so this makes this layer choosing problem much easier, right? So this is like, okay, I don't know how to choose which layer would be optimal for my task, so I am taking a really stack of the layers. Of course, one issue with this is that the feature vector, in that case we will get, this will become high dimensional. One possibility in that case could be if we can actually rank the features from particular layer. So we don't need to, in that case, take all the features from each layer, right? So let's say we have one layer and 56 features, another layer 56 features. Instead of taking all 56 plus 56, that is 112, if we have a possibility to actually choose 10 from one layer, 10 from other layer, the number remains controlled. So some of this conversation will come back when we will discuss unsupervised change detection, where the use of a pre-trained network as a feature extractor is common practice. And there, then these questions arise like which layer to choose, or can we form a hypercolumn, or can we rank the features from a particular layer. Now, let us move ahead to the idea of fine-tuning on target data. This is probably the most straightforward practice. You have, let's say, a network trained on imagined data, and let's say you want to now use this network on some Sentinel-2 dataset or some other dataset, let's say some Pleiades dataset, okay, another sensor, and you have, of course, you don't have a dataset as large as the ImageNet, but you have some training dataset on this target sensor or the target domain. What one could do is one could simply fine-tune on this target data. So in our case, the Sentinel-2 dataset. And it need not be only just sensor difference, it can address other kind of differences as well, right? Like let's say we are talking about Sentinel-2 datasets only. However, we initially we collected a large annotated dataset on summer images and we trained on those. Now we want to apply, let's say, on the winter images where we don't have that large scale annotated dataset. However, we have, let's say, small annotated dataset, which is reasonable to assume in most practical scenarios. So in that case, what one could do is one could simply fine-tune now on this target winter domain. Here also, the obvious question that comes is which layers should we train and which layers should we simply keep frozen. Generally, in most of the talks, what is done is that we just train last few layers, not more than that, whereas the initial layers, based on the assumption that the initial layers are capturing features that are probably generalizable across different types of data, that's why the initial layers are kept frozen. However, really depending on the task, you could also decide to actually fine-tune the entire network as well. Now we'll briefly discuss also about the unsupervised domain adaptation. At this stage, we'll not really talk about the specific architectures that are used for unsupervised domain adaptation. However, we will mainly talk about the problem setting. So the unsupervised domain adaptation, here the idea is that we have a source trained model and we have some data from our target domain. So in this case, the source could be, let's say, the summer images, the sentinel-2 summer images. The target domain could be the sentinel-2 winter images. And as I said that, okay, let us assume that, okay, it's difficult to annotate the winter images. However, we can, let's say, like collect some unlabeled winter images, okay? So the domain adaptation, the unsupervised domain adaptation setting here, what happens is this: we produce, using these two as inputs, we produce a target model which will now work reasonably on our target domain, that is in our case the sentinel-2 winter images. Now we'll take our discussion to the next level, that is what we started with. We started talking about the supervised learning paradigm, right? And there we discussed some architectures used for supervised training. Of course, the same architectures can be used for the self-supervised learning also, let's say. However, we discuss those architectures more like thinking, okay, to be used for supervised learning, right? And we also briefly mentioned about, okay, what kind of loss function could be used, let's say. And thereby the next question that we try to answer is, let's say we have this supervised model trained on some sensor, some domain A, and we want to use it for some sensor, some domain B, where we have, let's say, very few annotated data. How could we, and we don't even have annotated data, so there are different scenarios we discussed, right? That how can we use that supervised model on this particular target domain. Now let us think about unsupervised and self-supervised learning paradigm, where we will not use any supervision. However, we'll still be able to train our network such that the network learns meaningful feature representation. Once the network has learned meaningful feature representation, it can then again be fine-tuned on some very particular task, just as we have discussed a couple of slides back. Here, our first discussion will be on a mechanism called deep clustering. Before talking about the deep clustering, let us just take a moment to recall what is clustering itself. So if you have studied about, let's say, K-means clustering or some other basic clustering, you would remember that given some data, so in our case images, based on some feature representation of our data. Okay, so somehow let's say we have a feature vector of the images. We would group them into, let's say, some k number of clusters, so that each cluster makes sense to us somehow. Okay, so this is not exactly the classes that we talk about in the supervised learning setting. However, still each cluster, they should make some sort of sense to us. And following the similar idea, let us now extend to deep clustering, where the first step would be feature extraction, that is, use CNN to extract features from the input images. And we have to understand at this point that the CNN is what we are also trying really to train. So what shall we do? Like, given the input images, we are using this CNN to extract the features. What shall we do with these extracted features? We can simply use some sort of clustering algorithm to cluster the input images based on these extracted features into a number of clusters. So here I've shown 3. It could of course be a different number. So let's say we apply k-means clustering to group these features. Generally, the features are PCA reduced before applying the clustering. Now, the next step would be to assign pseudo label. What are these pseudo labels? These clusters, they will be now treated as different classes. So they themselves now can be thought of as this belonging to one pseudo label. It's like we give like label 0, label 1, label 2. Okay, so we are basically assigning them to like different classes. And now what we can do is we can use these pseudo labels that we have assigned to retrain the CNN using these pseudo labels. Okay, so here we see another branch of the network, okay, which is used for the classification, and then we use this particular branch for the back propagation as well. So to sum what we have talked about, this deep clustering, this is alternating between clustering the features to produce the pseudo labels and then updating the parameters of the CNN by predicting these pseudo labels. And this process will be done iteratively, that is, it will be repeated to progressively refine the features and the clusters. So here let us reiterate that clustering itself is not the goal. Clustering is acting as a signal to learn the embeddings. Embeddings is what we want to actually, we are interested in, right? A common empirical observation that is often seen during training of this deep clustering type methods. So The deep clustering, I will not say that this is just one method, there are variations. So in training, this kind of methods, what we see is that using more clusters, then the true semantic classes can easily improve the learned features. Okay, so why is it that? It's because there are, like, within the semantic classes, there are subclasses that the deep clustering often accounts for. Let's think about like building as one particular class, right? So most of the classification task, we will say that, okay, building, one class. However, building, if you think about this is not just one particular class, right? There are subclasses within this building class. So this needs to be accounted for in the declustering mechanism. That's why often using more clusters, then the true semantic classes can improve learned features. One of the challenge that is often faced when applying deep clustering, and also some of the other methods that we'll talk about later in supervised learning, is avoiding collapse or avoiding trivial solution. That is, you can think about like this, like all of the data you have like in images, and what could happen is that most of the data point could just collapse to a particular cluster, right? So these issues often is a challenge. We'll not discuss these issues at this point in details. However, if you actually try to apply deep clustering, this is something very important to keep in mind. Now, let us start talking about self-supervised learning. The supervised learning tasks have predefined, generally human provided labels. The self-supervised learning, they are often trained in very similar manner to the supervised learning. However, they derive their labels from some co-occurring modality or some property of the data itself. So often the self-supervised learning, they depend on something called pretext task. The pretext task can be thought of as a self-supervised learning task that is solved to learn visual representations. As an example, we can think about rotation of the images. Just think about your face image, okay? And what you could do is that the face image, you can now rotate at, let's say, like 90-degree angle, 180-degree angle, 270-degree angle, and they will look different, right? At least when we're talking about the face images. That is, you can think about like the passport size image that you take at a photo studio, and if you rotate it at different angles, you will be able to, like, even if it is given to you, you'll be able to guess like, okay, at what angle this has been rotated, right? So this can also be given to a network to guess like, okay, what was the rotation angle? Is it 90 degrees? Is it 180 degrees? Is it 270 degree? And this different rotation angle corresponding to different classes. The key assumption here is that the accuracy in the pretext tasks is closely linked to accuracy in downstream task. So generally, more difficult pretext task will satisfy this assumption better. Let us try to think about how a plot of effectiveness of the self-supervised learning versus the difficulty of the pretext task, this will look like. Just now I have told, right, that generally more difficult means the effectiveness of SSL is also more. Does this mean that we'll see like a linear kind of plot? Most likely, no. Most likely, what will happen is that with the difficulty of the pretext task, the effectiveness of the SSL itself will improve for some time. Okay, as you make the pretext task very, very difficult, okay, very challenging, at some point the effectiveness will again drop. So this is not a exact plot. The actual, if you actually try, like, do experiment and create one plot, this may look slightly different, but this is, however, approximately how we expect these to look like. Why is it so? This is because if the pretext task itself is very easy, then there is nothing for the network to guess, right? And if there is nothing for the network to guess, the network doesn't need to adjust its weights. We make the pretext task slightly more difficult, the network has to adjust its weights to learn this more difficult pretext task. We make the pretext task very, very difficult that it's even kind of impossible for the network to learn. Again, there is no learning signal, no real learning signal for the network. So with this, let us end our lecture here, and in the next lecture we'll continue our discussion on self-supervised learning. Thank you.